Hello, and it's my pleasure to welcome Dr. Yoshi Miyazaki.
Perfect.
Yoshi comes to us from Caltech via New Haven. Yoshi started at University of Tokyo getting a degree in Earth and Planetary Physics. He moved to Yale for his PhD working with Dr. Jun Korinaga. Developing, let's see if I can remember, developing a...
I don't even remember.
For terrestrial planets, and there's some words in between I practiced but can't remember right now. Yoshi is a geodynamicist and works on how things move on rocky surfaces and maybe other surfaces. Since 2020, when he got his dissertation in the pandemic, he has been the Stanback Fellow at Stanford in the Caltech Center for Comparative
Evolution.
Stanback Fellow, and he works on understanding the mantle. He's published on how water within the mantle will affect plate tectonics or how things move, mineralogy and things like that. He's published 15 papers, and 3 weeks ago he became a father.
Thank you. Oh, thank you.
Welcome, Yoshi.
Thank you. Yeah, thank you for having me. It was a great day 2 days not to be awake by my newborn. But again, thanks again for having me. Today, I would like to talk a little about how the volatiles surrounding us, the atmosphere, water, has arrived to the planetary surface, how it made its journey, mainly from a geophysical perspective. The reason I'm saying that is the conversation around this topic has mainly been fueled by a lot of geochemists and cosmochemists. But I want to say here is that there's a lot we can say by looking at the building of physical models and arguing what's the most plausible scenario from the eyes of the physicist. Now is really a great time for planetary scientists because we're not just finding a new exoplanet, but we're finding an Earth-like exoplanet in an habitable zone. This is a figure of a compilation of the old, it's a year and a half ago, but all the Earth-like exoplanets found in the habitable zone. Habitable zone is basically where liquid water can be stable at the planetary surface condition. So it can't be too far away, but it can't also be too close. And that's what's being plotted over here. But there wasn't news until recently saying that, oh, we found an Earth-like exoplanet in the habitable zone. That made a topic in CNN or those news medias. But now, I'm pretty sure in 10 or 20 years, we're just going to find many more. It's not going to be any great exciting news anymore. And the next real question is, how many of these are actually habitable? We all know that Earth scientists here, and a lot of people working in this field for a while, are working towards understanding how these habitable systems can even be maintained on Earth. That means having this planet, putting it over here in between this red or blue or yellow-blue zone, means they are actually habitable. And so the very minimum requirement here is that obviously these volatiles, including carbon and nitrogen, but basically water, especially water, has to be delivered to the planet, especially to the mantle. I will get into that later, but especially to the mantle. And those has to get out from the mantle and form an atmosphere and oceans. Obviously, Earth suffices all three conditions, but the planets that I showed you in the previous slides, do they have enough water to be delivered, and are they actually in the atmosphere and ocean to form a habitable surface environment? That is a totally different question. So that is a very big topic, so I would like to kind of focus on two narrower questions over here regarding how did water get delivered and how it actually degasses to the surface. And the questions I'm actually asking here is, first one is when and how do volatiles get delivered to Earth, or how did the volatiles get delivered to Earth, how do in general to the terrestrial planets in general. And the part two is more like thinking about how those delivered volatiles get out of the mantle in the interior and form a habitable surface environment. This is really a part of the larger effort to understand Earth and other exoplanets, terrestrial exoplanets, the process of them acquiring the habitable surface environment. The reason especially I want to focus on this topic is because how we think the volatile got to our planet, water and carbon got to our planet, has really been changing in the last 20 to 30 years. This is a real classical views that a lot of people imagine in 1970 daisies what we thought it happened. So initially, when the solar system were formed, it was no planet. This was a mixture of gas and dust particles, small dust particles still not being formed as a planet. Water existed throughout the disk, but it was only in the region really far from the sun that water existed as ice. It was water vapor in the inner region. So as it grew, only the outer region formed, had ice as a building blocks. And at the end, what we thought it would happen was water-rich planets basically made out of ice, and the outer region, inner region made out of maybe rocky, dry materials. So what this implies was that we thought water has to be delivered at the final stage of planet formation. Planet was formed dry, and water was delivered through maybe through comets or water-rich asteroids that delivered the water to these bodies. And these regions separating these two lines, where the ice started to condense, is what we call snow line. That's what it's drawing over here. But this idea is really rapidly changing. I can show you many other slides or data for it, but I was just rather focus on one here to kind of emphasize the importance. What I'm showing here in the right is what we say isotopic composition of ruthenium. And we know that this element arrived after the moon forming giant impact. So that means the ruthenium arrived in the real last moment of planet formation. But if you look at this composition, you see a similarity between what Earth's mantle and enstatite chondrites. And this shows that last bit of the Earth's formation was driven probably by enstatite chondrite-like material. But the problem is, among all chondrites, this is a type of the asteroids, but we know that among all these chondrites, enstatite chondrite is the driest material chondrite among all of these. And simply adding what we think we added after the moon forming giant impact is around 0.5% of mass of their present-day Earth. But simply adding 0.5% of enstatite chondrites can only account for, at most, 10% of what we have on Earth. The words it says over here is bulk silicate Earth, but that means we have what water amount we have on mantle, crust, atmosphere, and ocean. Anything in the Earth, but excluding core. So I was talking about the late delivery. Well, maybe the moon forming giant impact can deliver. That seems, I wrote a paper on this, but that also seems like an unlikely scenario. And moreover, I mentioned the word snow line, where the ice starts to condense. But now these models are showing is that this ice snow line has actually existed around us, like 1 AU, at one point during the Earth's solar system history. So what that means is that when the Earth solar system was forming, we actually had a lot of ice around us. So the idea that it created dry and water came late in the history is probably wrong. It's rather than our solar system was forming, but volatiles, water, was always being around us, and it has been added throughout the history of Earth's formation. So that really forces us to change a lot of our understanding of the planet formation. Water or carbon can act as a huge changing mechanism for a lot of things during planet formation. So the question I want to ask here is, when and how did volatiles arrive? And for here, I'm actually going to turn a little to what we call a refractory siderophile element. What siderophile elements are, what this basically means is iron-loving elements. So from the next 10 or 15 minutes, I'll be talking about siderophile elements. But the reason for that is volatiles are also iron-loving. When these impactors, so when planets, we're thinking about planet formation, planets is growing. So when that happens, like impactor hits the growing body, when that happens, the gravitational energy is released, so you produce a huge amount of mantle melting. So what that results is that you have a lot of melts, impactor's core, this metal area is being delivered. So there's a very efficient reaction between what's coming in as a metal part and the target's mantle. So basically metal silicate reaction. But when that happens, when there's metal and silicate coexisting and reacting, all the elements that really love to be in iron will kind of rush into the metal phase, and they will basically end up in the core rather than staying in the mantle. How iron-loving, how siderophile the elements are is what we describe by this D value. But D value can be as high as 1,000 for elements like carbon. So it seems, when I say, okay, volatiles are delivered throughout the history of Earth's accretion, it seems like it's easy to have volatiles, but it's actually not. Because a lot of the volatiles, as it's being added, it can be simply stored in the core rather than being left in the mantle. So I want to understand this process. How did volatiles escape this process and be stayed in the mantle? We obviously have that because there's a lot of volatiles around us. I want to understand the process. So tracking volatiles, however, it's difficult because it can be lost to the space, it can be lost from the atmosphere. We don't know how much it got added in the first place. So for that reason, because it's both are siderophile, iron-loving, I will be focusing on refractory siderophile elements in the next 10 or 15 minutes. But I will promise I will come back to volatiles. I will make a connection later. But for the sake of argument, let me allow to talk about not volatiles, but siderophile elements in the next for a little while. So this figure, what I'm showing over here, is what summary of how we think about when iron-loving elements arrived on Earth's mantle. This is a famous figure from Nicolas Delfosse, University of Chicago professor, a 2017 Nature paper. It's really well cited. But what this figure shows, if you look at the x-axis, this is basically it's growing with time, mass accreted. At the right end is the present-day Earth, and it's growing from left to right. But you can see that it's basically 0 for the first half. So what that means is that Earth was once half of its side. And during that period, also material was being added. And those materials probably contain a lot of minerals, elements like nickel and molybdenum. But all of them were basically partitioned to the core, to the metal phase, and lost to the core. So if you pick up a rock and find the nickel and molybdenum in this present-day mantle, those were basically delivered during the real last stage of planet formation. So if we find a nickel and molybdenum in the mantle, that means we're seeing some signature that was accreted later during the Earth's accretion. So then the idea here is that the more iron-loving, more siderophile elements are, the later it got added to the present-day mantle. That is the present-day understanding, and that has been used as a framework to understand a lot of data. And I won't go into too much of the details, but the basic assumption of this model is that the growing protoplanet, that when the planet Earth was growing, it had what we call a very deep magma ocean. So what the idea is that these growing bodies, Earth is growing, but basically had a very thick layer of melt layer, what we call a magma ocean, and we thought it was deep. And that is the assumption of making the figure in my previous slide. And if that is the case, an incoming body will melt in the magma ocean and equilibrate, basically metal and silicate, metal in this part and the silicate up here, will react at the deep part of the mantle. And that was the kind of the assumption being made. Why are we making this assumption? It's because we think we need this for explaining the elements of nickel and cobalt. Nickel and cobalt are really, really iron-loving at like the shallow mantle condition, like around us. If you make them react metal and silicate and put nickel in it at like low pressure, basically all of the nickel and cobalt will go to the metal phase. That's what it means when this D value can be as high as 1,000. But if we look at the mantle, we find a lot of nickel and cobalt, what that means is that these elements shouldn't have been that much iron-loving. And there has been a huge debate, how can we explain this in early 1980s to early 2000? And the solution probably, we thought it came from high-pressure community. What experiments show was that if you see the partitioning coefficient of these elements, it becomes smaller and smaller, which means that these elements do not love iron that much at a higher pressure. So that means metal silicate reaction equilibrium should have taken place at the deeper mantle, on average 40 to 60 GPa. And for that to happen, people drew this cartoon. So the growing planets should have had a deep magma ocean, and that's where all the reaction was taking place. But it seems like a very nice picture over here to explain that data and to come up with that story. But I have to be really careful because the reality can be a lot more complicated than that. And the reason I wanted to poke on this was this model that I showed over here is actually only based on the figure I just showed you. It was kind of developed to explain the nickel and cobalt abundance of the mantle and not much else. And yet, there is a lot of kind of physical controversial assumption in terms of geophysics. One is that those models assume that every kind of body falling onto the Earth, it was established some sort of metal and silicate reaction as it kind of was forming. And also the other obvious assumption is that there should be a lot of melting on a growing protoplanet. And those two, especially these kind of growing protoplanet has a deep magma ocean and it's survived throughout the history of planet formation. That is a big assumption. And actually I want to question those two in the next 3 or 4 slides. So that's what the kind of my latest paper are doing with a collaboration with people at Caltech. The first part is, as I mentioned, I was talking about if degree of reaction between metal and silicate. And the kind of models I showed in the earlier slide, it kind of assumed that the incoming body is always reacting with the mantle, and that produced the signature of what we see in the present-day mantle. But in reality, it's much more complicated. This is the model accretion history birth. This is some sort of what we call n-body calculation. We're tracking what is going to be Earth at the end of the accretion. That's time and x-axis, running for 200 million years. And you see that Earth is kind of growing and becoming Earth-sized. The mass is the y-axis normalized by the present-day Earth mass. If you see this, it's not like monotonic kind of nice slope. It's rather than you see a huge jump in some places, which means that Earth accreted through several giant impacts. So this around like 2.5 Earth mass, 25% Earth mass, 15%, 10%. So basically, Mars-sized or double-sized Mars-sized object was kind of hitting the Earth, and that kind of jumped up the Earth mass. But that is really inconvenient to think about how iron-loving elements being added to the Earth. The reason is that this is kind of a snapshot of what happens during these giant impacts. This gray area is the core material. But when these two collide, basically you see that these are distorted, but iron core of impactors and targets, they basically stay together, which means that core is staying with core. They're not really mingling. So metal and silicate are not basically reacting that much. So these two core basically merges without much of the interaction with the mantle. So basically, there's no element exchange happening during these giant impacts. And these giant impacts will create a really energetic impact, so it will create a deep magma ocean. But those deep magma ocean can really solidify in a very rapid time scale. What characterizes, it's maybe hard to imagine, but there was Earth was also once had a completely molten stage. And how fast those magma planet solidifies, it's really determined by the atmosphere side, atmosphere's greenhouse effect. And the greenhouse, right now the most important greenhouse will be CO2, but in these kind of contexts, it's the water vapor. So it really depends how much water vapor we have on the atmosphere overlying a magma ocean. This figure shows how much of the water is remaining in the mantle, remaining in the atmosphere rather than being exhaled to the silicate magma. Water is one of the most soluble volatiles we can think of in all the CO2, H2, CO. It's among those. Water is the most soluble. And if we have a magma planet and if we have some water around the mantle and atmosphere, basically more than 99% will be dissolved to the magma ocean rather than staying in the mantle. This shows the x-axis the radius of the planet. So this is around Mars size. This is around present-day Earth. But if you have a magma planet of these sizes, basically all of them, and this trend is more significant for a larger planet, but with less than 1% will remain in the atmosphere. So what this tells us is that magma ocean, atmosphere on top of a magma ocean is really, really dry. We don't have a lot of water in there. And this matters because this figure shows how much heat can be emitted from the top of the atmosphere from the magma ocean. Basically, the higher the number is, that means it's emitting a lot of heat, so it solidifies really, really fast. I'm showing 3 lines over here. Of course, when there's no atmosphere, no greenhouse, so it really solidifies fast. But even if you compare these 2 lines with water for CO2, having like different amount of water can change this heat flux by nearly 2 orders of magnitude at some conditions. And a lot of the previous model has assumed that there's going to be a lot of water vapor atmosphere on top of magma ocean. But if you think about the solubility, if you think about how water is soluble to silicate magma, the atmosphere is really, really dry. And that means there's very little greenhouse effect. And the magma ocean can solidify very rapidly. Actually, I will delve into the model a little more deeply, but I want to first kind of outline the story. So I would just say that I built a model combining magma ocean and atmosphere and solve for the solidification timescale. And in these kind of growing embryos, in a growing protoplanet, we have a giant impact, it completely melts. How quickly would it solidify? We get a number around 50,000 years. So after an impact, magma ocean basically solidified within 50,000 years. But how often the impact comes? Like, I'm counting every single impactors, like even the small ones. It only comes every like 0.1 million years at the early stage. So this tau is like age of the birth from the solar system. But towards the end, we only get an impact every like 1 million years. So it's simple timescale comparison. Solidification happens much faster than the next impactor is coming. So what they can imagine is that growing planets, we often think that it's a kind of energetic process, and the protoplanet is covered with magma ocean. But actually, these planets are basically, when the impactor is coming, they're basically mostly solidified. Impactors melt, creates a huge magma ocean, but it really quickly solidifies. And by the time the next impactor comes, it's mostly like a solidified planet. What I'm showing over here is, I had a blue colored here, but so what I mean by is that each dot comes every like 0.1 million years. You have a huge deep magma ocean created after a giant impact, but it basically solidifies before the next one comes, even the small one comes. Of course, these small impactors also create some amount of mantle melting, but the amount of melt, basically magma ocean, volume of magma ocean created by an impactor is proportional to the kinetic energy of the impactor. So these large ones can create a lot of whole mantle scale melting, but these small ones can only create at most like 400 kilometer depth pond. And the pressure that reacts with a silicated metal is around 13 GPa. If you were focusing and still remember that my earlier slides, the value needed to explain nickel and cobalt was like 40 to 60 GPa. What we see is like even in a kind of optimistic case, these impactors and impactor's core and the silicate body will equilibrate only at like 13 GPa. So it's very hard to imagine the scenario that these metal silicate equilibrium reaction during the planet formation is taking place at the deep part of the mantle from a physical perspective. So I don't want to kind of double down again, but these whole scale magma ocean can solidify within 50,000 years. Of course, small impactors will create some amount of melt, but it's very small amount, and it's such a small amount, so it rapidly solidifies within 1,000 years. This is much shorter than the interval of impactor. So again, growing planets will basically have a solidified surface for most of its time period. And that's a problem for explaining this this value over here. The idea was that these elements have to equilibrate at the deep mantle to explain the present-day mantle. But in no way scenario, we can think about a scenario that these elements are reacting at the deep part of the mantle. This was the picture. We have a deep magma ocean, and metal and the silicate was reacting in these kind of deeper part of the mantle. But the more likely scenario, if we simply run a physical model, we basically have an impactor coming in, but maybe some amount of melt, but very thin layer at the top. So that is very inconvenient to explain how this nickel and cobalt has been so enriched in the present-day mantle. Why is that? So I decided to revisit this problem last year, and this is a work done with one of my summer interns at Caltech. So we decided to incorporate the realistic growth of the n-body calculation. We thought about the realistic degree of metal-silicate reaction during giant impacts, and also after each impact, we solve for how quickly these magma motions solidify, so that we get a physically self-consistent evolution model. This over here is based on the previous idea of deep magma motion model. X is a mass accreted, so basically Earth is growing from here to there, and how the nickel and cobalt concentration is changing with the planet mass is plotted over here. Nickel is on the left, cobalt is on the right. And you see, it's really low in the beginning because it's really, really iron-loving in the beginning. But as it grows, we thought that planets will develop a deep magma motion. They will react to the high-pressure region, so they quickly increase their abundances and reach the present-day mantle value at the end of the accretion. So what this figure tells you is that, again, I showed it in the nickel-Adele-Fuss plot, but most of the nickel and cobalt in the present-day mantle has been added during the real last stage of planet formation. That was the idea. But again, this really ignores all of the assumptions, all of the physical considerations that I showed over here. And if we incorporate those, we get a value much smaller than that. The reason it's again so smaller is that everything is reacting at the shallow mantle. So it's really iron-loving, and you cannot add a lot of these nickel and cobalt, these kind of stereophile elements, to the mantle. So if from a physical consideration, we thought we solved this problem of having too much nickel and cobalt in the mantle. But again, it doesn't seem very likely to happen from deep magma motion model. It doesn't seem to hold. And if we run a more realistic model, we have a shortage. You cannot explain a nickel and cobalt. There's too much nickel and cobalt in the mantle, of at least factor of 3 to 5. It will be irresponsible to say, okay, there's a problem, and so I'm going to provide what I think could be a more realistic solution to this. The answer is that I think that the origin of these stereophile elements are being really simply direct embedding of the impactor's core. What I mean is that on the previous models, all the models assume that it comes in, metal-silicate reaction takes place, and the metal phase will sink to the core. But that's not necessarily the case if these growing planets are mostly solidified. As it hits, basically it kind of fractures, and these metal in this impactor's core will be retained in the upper mantle. And there's been a lot of theories to support this. My PhD advisors wrote that metal can be trapped in a partially molten silicate, or there's also been other suggestions saying that there could be a lot of ferric iron, Fe3+, in the upper mantle during the growing stage. And those Fe3+ can react as Fe and become Fe2+, ending up basically all of these core being retained in the mantle chemically. And if we simply have like 6 or 10% of chondritic materials, that's original material we had in the solar system, but if we add not just the silicate part, but the metal part into the mantle, we can easily explain a lot of these nickel and cobalt, chromium, that's the other moderately solidified element, but the abundance of those elements in the present-day mantle. So what this means is that, and if you look at the model accretion, details differ from the model, but every model shows that we have giant impacts and small planetesimals being added in the middle. And those planetesimals can simply be added to the mantle and be the source of siderophile elements of what we see in the mantle right now. I'm going to be, the next few slides are a little more convoluted, so I'm sorry if it gets confused, but of course it's not the end of the story, because once it's become embedded, it's going to remelt after the giant impact, and These dots represents to what's being added during this stage of small planetesimal accretion. And after that, we have a giant impact, and we melt a huge amount of, we create a huge amount of magma ocean again. And of course, there will be some sort of metal silicate reaction taking place, but that's actually not going to affect the siderophile element budget that much. Why? Because we're talking about a small amount of metal reacting with a huge amount of silicates. This figure shows how x-axis is the partition coefficient. So elements on this side doesn't really love iron that much. On the other end, they will immediately go to the iron phase, metal phase. And the y-axis is how much of them will remain in the mantle after metal silicate reaction. And what we see on the blue line over here is that the scenario that's more likely during planet formation, we have small amount of planetesimals being added to the upper mantle, and those small amount of metal will react with a huge amount of silicate magma ocean. So in that case, even like elements with partition coefficient of like 100, that's pretty iron loving. But those elements will still remain in the mantle after metal silicate reaction take place. And this is very different from a kind of really simple model that's being often used, which is taking this red curve. Red curve means like we have reacting like entire core of the present-day mantle and present-day Earth and the entire mantle of what we have right now. The mass ratio is around 1 to 2. So but if we react that huge amount of metal with the silicate, that will kind of immediately suck up all the iron-loving elements that have anything d value larger than like 10 or 100. So what I want to show over here is that if these siderophile elements have been added by small impactors, that means even if we were to melt subsequently and undergo a metal silicate equilibrium, they can really remain in the mantle. I'm sorry if I get lost to you, but the key point is this. Because magma ocean that's growing, that's formed on a growing protoplanet solidifies so fast, when the small planetesimal size impactor, that small 100 to 1,000 kilometers body hit the Earth, those core materials can really remain in the mantle rather than being delivered to the core. That's very different from when Mars-sized impactors, what we call giant impacts, happen. When Mars-sized impactors happen, these cores will really directly go to the core. But the small ones can be embedded in the mantle, and that could be the more likely the scenario what we see in the present-day mantle. Why does this matter? Because what I'm saying is that if we find a siderophile element, iron-loving element in the mantle, what I'm saying is that that's a tracer of small impactors. And it has nothing to do with the timing of delivery. Nothing is a little overstatement, but basically has a very little correlation with the timing of delivery. That is very different from the original model, which said that if we find a siderophile element, that is a tracer of materials that's being added during the late stage of accretion. What I'm saying is that it really more matters how it's being added. So what I'm saying is the signature of small impactors. So if we start to say, when did it get accreted, we might be asking a wrong question, because it might more rather be about how these elements got delivered to the present-day mantle. Why does this matter so much? Because it's being used in a lot of framework. This kind of siderophile element framework is being used in a lot of interpretations. This figure is a isotopic composition of molybdenum. That's one of the, I was showing over here, but one of the siderophile elements. And I will try to explain it kind of qualitatively here, but we know there's kind of two components in Earth building block of the Earth, what we call a CC, carbonaceous chondrite, and NC, non-carbonaceous chondrite. And we found that for molybdenum isotope, we need half of each to explain the Earth's isotopic composition. But if we combine this with this deep magma ocean, what this shows is that because we thought the molybdenum was added during a late accretion, what this data suggested was that, okay, last 10% of Earth's building block has to be half CC, half NC. But if you think about what happened during the last 10% of Earth's accretion, it's a moon-forming giant impactor. So the interpretation was that, oh, moon-forming giant impactors have to be what we call at least contain a significant amount of carbonaceous chondrite. But the problem was that it was really hard to reconcile that fact with what we know from the other more planet growth model. We don't see anything. Carbonaceous chondrite material is coming from further away from the Jupiter. That's what a lot of people think, not everybody. But we cannot find any kind of scenario that kind of matches with it. Those people were coming up with really creative thing. But if you think that these signatures of molybdenum is coming from small impactors, it might much rather easily explain how these molybdenum got added to the present-day mantle. And that's where, in the last slide of this first part, I'm coming back to the talk. But the material coming from really far away, the Jupiter region, the carbonaceous chondrite, we know it's more likely to be enriched in volatiles. And having those materials being delivered to the Earth's mantle through carbonaceous chondrite will naturally explain the amount of volatiles we see on present-day Earth. So I try to kind of focus on a qualitative thing. In this paper, what I do is a lot of kind of timescale analysis of physics, how much of the metal reacts with the silicate. That's a kind of a detail, so I didn't go much too into the details, but I hope I was able to show you, by actually thinking about the physical process of planet formation, the kind of common idea of deep mag motion model is not necessarily true. And how we can trace back the siderophile elements to what we got added could be traced back to what we see accreted as a small impactors. I am running. I'm running a little late, so that's the first part, and I would want to tune the gear a little bit and focus more on how those delivered volatiles will get out of the mantle and form an atmosphere. And the reason this is another question is because there's a lot of argument about early Venus. There's a lot of studies saying that maybe the early Venus was a habitable planet. Of course, if present Venus is out of the question because it's too close to the sun. But we know that in the old days, sun was a little weaker. So some people think that these early Venus was inside the habitable zone. But again, if we put the present-day Venus composition to the habitable zone, there had no water, too much CO2, so it can never form an Earth-like condition. So the question is, how did these atmospheres form? And that's the question I want to answer over here. And I would like to jump to the last giant impact. This is what we think happened during the final stage of planet formation, moon-forming giant impactor. And that will create a significant amount of mantle melting. And the reason I want to focus here is that when the mantle is that much molten, there's a huge amount of exchange between the atmosphere and the mantle during this period. Why? Because the convection, the convection that's transporting the heat, basically goes from these convection will transport the material from the top to the bottom to the top again in a matter of weeks. This is like 3,000 kilometers thick, but that could convect back and forth in a matter of weeks. So it really kind of resets anything volatile budget that's happening between here, atmosphere, and the interior. And this determines this balance between atmosphere and mag motion? It's the solubility. How soluble it is to the silicate magma will determine how much water is in here versus what's in there. This figure shows that as a function of pressure and how soluble it is. But for the magma ocean conditions relevant to Earth, water is really, really soluble, as I mentioned in the earlier slides. So if we employ this solubility law and get a rough estimate, we now know that we can calculate that more than 99% of water, this is what exactly I said in an earlier slide, but will be in the mantle when the atmosphere will be really, really dry and doesn't have much water in it. On the other hand, CO2 is very different because CO2 is not that soluble. So 70% will exist in the atmosphere rather than stay in the mantle. And this really sets the initial atmosphere for at least for a few 100 million years, maybe for 1 billion years to come. Why? Because if this amount of volatile amount in the atmosphere in the mag motion won't really change even as the mag motion solidifies or as tectonics happen. The reason is that when magma motion solidifies, it's not like water solidifying that you can only one phase and ice grows from the bottom. It's rather that when it solidifies, it gradually solidifies. You may know from thinking about the magmas, but some crystals start to form. At one point, there's too many crystals, and crystals start to get interconnected. They will have a lot of melt pocket inside of basically mostly rocky material. That's what I call mushy layer. But in this kind of mushes, you have a lot of melt pocket incorporated in. And these melt pockets can contain a huge amount of volatiles. So these kind of melt pockets can create water, a lot of water in it. And if you want to get these out to the atmosphere, you have to you have to push these melt out towards the surface, and towards the surface to the magma layer, and those magma volatile in this magma layer has to go out to the atmosphere. It's a kind of a two-stage process. But that condition is not necessarily met in such a deep kind of profound magma ocean. You might think like, okay, these kind of partial melt can easily escape towards to upwards and go to the atmosphere. But if you look at the more details of the mineralogy, that's not necessarily the case. Why? It's because melt can actually go downward. Melt versus solid, actually melt can be heavier, denser than the coexisting solid. Why? Because this is kind of a partition coefficient. It's a more distribution coefficient. But with higher pressure, this is x-axis of pressure, but if you go to high pressure, iron goes more and more into the melt. So that melt is so enriched in iron that it becomes heavier than the coexisting solid. So when melts want to move, migrate towards this mushy layer, it goes downward rather than trying to reach to the surface. So deeper part of the mantle doesn't have an upward migration of the melt. And on top of it, even if it was kind of in the shallow region where melt wants to go upward, these melt migration have to happen faster than the solidification. If the magma mantle solidifies really quickly, they don't have enough time to escape this mushy layer. So these two conditions, so that's what I want to check over here. Does the melt migration or solidification, which is going to take place faster? If the melt migration takes fast enough, then that means you can have a lot of water get out of the mantle. But if it solidifies really fast, all the water can be kept inside rather than forming an atmosphere. So this is what I actually do. So I'm forming a couple dynamic model of atmosphere, magma ocean, mushy layer. And on top of it, where these boundaries form and how much melt exists, we have to think about the chemistry. So that's why I'm incorporating a phase diagram model that I developed during my PhDs and solving all of these equations in one model to have a self-consistent understanding of how magma ocean and atmosphere co-evolve together and determine the initial atmospheric composition. This is kind of a rough summary of the result. Left plot is temperature, melt fraction, and the water content in the right. So basically, this is a pressure. I have a better slide in the next one. Kind of not a pretty one, but at least I hope you get a better idea of it. So we're talking about the surface at the top and the core mantle boundary on the bottom. This is temperature. And this dashed line is where it separates the mushy layer versus magma ocean. This is when crystals start to get interconnected and trap all the melt. Now, as you can see, this is a water amount, but you see that this water is not really changing near the surface. Why? Because all these kind of partial melt are going downwards because melt is really heavy. So melt is being delivered to the bottom of the mantle. You see a melt fraction increasing as well, and water content is high. So all the water in the deep mantle is transported towards the core mantle boundary rather than towards the near surface atmosphere. And that continues. So we have a lot of melt in the deep mantle. At one point, if it comes to like 40 to 60 GPa, melt starts to go upward. And you see that you see a slight increase in water content in the near surface mantle. But from this stage, this mantle starts to solidify really fast because this curve is kind of characterized by the solidification curve. Like as the magma ocean solidifies, it kind of gets anchored at the melting temperature. But this melting temperature is steeper than the adiabat. So what that means is that this mushy layer is unstable as it forms and really kind of mixes really fast and solidifies rapidly. So I would that might be too much detail, but as a conclusion, what I want to say is that magma ocean, this kind of lower mantle, can mostly solidify within 30,000 years. magma motion really solidifies in a rapid time scales. And so that melt migration is too slow for water to be kind of sucked out of the mantle, and most of them are trapped inside. What this over here showing is that 80 to 90% of water that was initially in the mantle stays in the mantle even after magma ocean solidification. And this really matters for many degrees because, as I mentioned earlier, water is a really important greenhouse effect. If you're keeping water in the mantle, you have a dry mantle, and the mantle magma motion solidifies really fast. 1 bar, 100 bar, 10 bar, 100 bar, different atmosphere will have a very different solidification time scale. And this really creates an interesting physics because if water is really largely retained, you create a dry atmosphere. So magma motion solidifies really, really fast. So that would allow for rapid cooling of the magma ocean, and that will not give you enough time for melt to escape. That means you are keeping more water inside the mantle. There's a positive feedback going on over here. Somehow a lot of models assume, existing models assume that water can get out easily and form a wet atmosphere, but that will implicitly assume that you have a slow cooling, you have more percolation, and more water degassing. And why is this unlikely? Because, as I said, water delivery to the surface is driven by melt migration. And melt migration also creates a differentiation of the mantle. If there was so much water being degassed, that means you will create a very thick melt layer at the bottom, and you will have a very fractionated mantle layer near the surface. And they will have a very different consequences. One is super wet, weak differentiation, mostly homogeneous, thin basal magma motion. But the other end is like very dry, strong differentiation, and really thick basal magma motion. And this is very unlikely because we know in the present day mantle, we don't have such a thing. If this kind of thick basal magma motion existed, we will see a huge heterogeneous layer at the bottom of the mantle, but we do not see such things. So what's more likely scenario is that mantle kept most of the water during magma motion solidification. And that is a more likely scenario of the planet of the terrestrial evolution. Then now I'd like to link a little to the Venus of what I just talked about. So this what shows is that when the kind of terrestrial planets evolve, most of the water can be kept inside a mantle, while CO2 is largely released to the atmosphere. And in that kind of condition, this is a controversial topic, but a lot of people, not a lot of people, but quite a few people believe that water is really crucial to triggering plate tectonics. If water was absent in the surface, that means there's no plate tectonics, and we will turn into what we call a stagnant lid convection. That's what we see on Venus. There's surface is covered with one thick lid. In that case, we don't see a lot of convection reaching the surface. So what that means is also degassing of the mantle is inefficient. That's really different from plate tectonics. Plate tectonics, if you go to Iceland, mantle material is reaching the surface, and which means that all of the volatiles, water included in the mantle, will be released through the volcanism. If it was turned into a stagnant lake convection, that means there's a really slow release of the water. This is the x-axis of time. Now it's a billion-year time scale. It is how much water get degassed. But initially, we only have like 10% ocean mass. But even after 4 billion years of tectonic evolution, we will only have like 30 to 40% of water that was contained in the mantle be released to the surface after the atmosphere. And if it's this slow, and if it was that close to the Venus, you can lose most of the volatiles, water. As we get the gas to this atmosphere, it can be loosed towards the surface, to the space. So that's what I'm suggesting over here is that Venus could have a water inside. It could be degassing a little bit, but it could be lost as it gets degassed. And that's the state of the Venus, what we see right now. So what I showed here is that when the magma motion is formed after the moon-forming giant impact, that's what we believe would happen for Earth or Venus, the atmosphere was extremely rich in CO2, but very dry in the atmosphere, and most of the water was contained inside the mantle. And the natural consequence, if it were kept and there was no plate tectonics, the natural consequence of the evolution is actually like Venus-like. We have a very thick CO2 atmosphere, very little water. We don't know how much water is in there, but I believe there could be a substantial amount. And that would be a more natural consequence of planet evolution. There has to be something special to be able for planets like Venus to turn into more Earth. And can we kind of test this idea? Probably. That's one idea, is that we're going to Venus in the next decade, and there's 2 missions at Veritas and Da Vinci, and they will see how much water there is still inside of the Venetian mantle, or how much water is being lost right now. And these kind of clues can be a very strong tool to kind of narrow down what's happening in the early Earth evolution or early Venus evolution. And on top of it, we're going to have a lot of exoplanet observation in the coming decade. If what I'm saying is true, that means if you look at a lot of Earth's atmosphere, Earth-like atmosphere, Earth-like exoplanet atmosphere, we'll find a lot of CO2 rich atmosphere with very dry ones. That will take probably another 20 or 30 years to get that much amount of data, but that is something what I expect to see. That's just the end of my talk, so I will kind of, I just want to comment a little about what's so special about Earth. Probably Earth had a very fast plate tectonics. That's kind of one of my paper. Earth, if I could see this red curve over here, that's what I believe, but Earth could have had a plate tectonics. Mantle temperature at the beginning was like 1600, so that shows a plate velocity. Yeah, go ahead.
Sorry, when you say fast plate tectonics, do you mean that plate tectonics began relatively fast compared to other planets, or that they occur fast?
That's a great point. What I mean is like plate velocity was fast. So if plate tectonics was happening in the really early stage, the velocity could be as high as 50 centimeter per year. That's what I showed in this paper. And that could really remove, maybe have heard of carbon cycle, but really fast carbon cycle that also release a lot of water from the inside and quickly turn the Earth's state, Venetian state like the atmosphere, into Earth-like state. Why would that Venus never happened? That didn't have it, Earth had it? I don't know, but there's multiple reasons we can now point to. Maybe Earth received weaker solar radiation, so we have easy to have a water, or maybe it was farther away from the sun, so maybe it was we had more water to start with. And another difference might be Earth has a moon, but they don't. And moon can have a huge impact on the thermal history plus the degassing history. So moon could have helped water get out of the Earth's mantle and form an atmosphere. We don't know what was the case, but if it happened, plate velocity can be happening very fast, and that can be the solution to explaining avoiding a Venetian state as a result of magma ocean solidification. So that's kind of the main 2 points I want to deliver. Anyway, volatiles. So what I suggest is like volatiles were delivered by small impactors, and those volatiles they were mainly before moon-forming giant impactors, and those volatiles can be largely kept, especially water, inside the mantle. CO2 will degas, but water will stay in the mantle, and Venus-like state might be a kind of a natural consequence of planet formation. What I really focus on is from the growth stage towards what happens after the moon-forming giant impact and starts into like present-day Earth-like surface evolution. I try to solve that through geophysical modeling, not just focusing. This is what I just showed over here, but not just focusing on like one kind of reservoir, but thinking about interactions between different reservoirs, mantle, atmospheric core, maybe different phenomena like impacts, core formations, magma oceans, and try to tie with phase diagram and link with data we have in cosmochemistry, petrology, or high pressure experimental data. That's what I use. And potentially, the big picture goal is to link with upcoming emissions or exoplanet atmosphere observation that we expect to have in the next decade. I'm kind of running out of time, so I will skip. I'll skip here, and I was to thank my advisors and collaborators who were involved in my work that I showed here, and I would like to take questions. Thanks.
There's a question from Lucio in the chat.
Oh, okay.
You might want to push. It's rather long, so.
Let's see. Can you get to chat? What about it?
Yeah. No.
We're going to do Luju's and then Claude.
I can just read.
Yeah.
We don't have to figure out how to bring it up.
Oh.
So, Luzu asks, a critical component, by the way, nice talk. Thank you.
Nice.
A critical component in thermal evolution models is the thermal conductivity, which undoubtedly changes with pressure, temperature, and composition. In your time-dependent model, in which these parameters will likely change, how are you treating the evolution?
Yeah, great question. So what I'm actually, so the critical part is not the thermal conduction, it's the convective movement, or like a Rayleigh-Taylor instability, like a movement of the mantle that's really driving the thermal evolution. So I'm not really incorporating the thermal conductivity over here. But obviously, you can also think about something called effective thermal conductivity. That means how efficient the heat being transported within the mantle. That depends on the viscosity, water content, and a lot of parameters. So I do play a wider range of the parameters when I publish the paper. So I get some scenarios that we can keep on most of the water in the mantle, where I get some, in kind of extreme cases, kept some of the most of the water being degassed. But when I do the kind of wide parameter range space, I see 90% of the likely parameter space kind of falling onto the water being kept side to the mantle. So that's what I'm kind of presenting over here. I hope that kind of was being heard by Luju and answers his question. Yeah, thanks.
Claude.
Thank you very much. Interesting talk. I think there's quite a few things I don't understand here. I'll just focus on one.
Yeah.
As you say, water is important in plate tectonics. And in the early Earth, most of the water was in the deep mantle. How could there have been plate tectonics in the early Earth?
So most of the water is in the mantle, but it really. So what I showed over here is like roughly 10 to 20% can be released to the surface. That's kind of a borderline for forming like significant water oceans. It might, I think it's a possible scenario that 10 to 20% was sufficient to form an ocean. That kind of triggered the plate tectonics. And then once the plate tectonics is triggered, it's kind of easy to get the water out. So that's what I envision what happened for Earth. That I think that did not happen on Venus. We maintained a stagnant lake convection stage. With little water kind of amount would kind of maintain throughout the history.
And one last thing, can you explain to us the mechanism, the physics behind why water can break lithospheric plates? That most water that makes the lithosphere.
So I cited a couple of papers over here, which all suggest the potential. All the papers says water is important, but all of them actually advocate for different mechanisms. And so this is not a set argument at all. We don't really know why plate tectonics happen yet. But the reason I brought it up is because quite a few people think in a different way water can be important. One of the ways is like water-rich sediments can lubricate the lithosphere. Another way, like my PhD advisor is kind of advocating, I think you may know, but it's water kind of promote the cracking of the lithosphere, kind of weakens the strength of the lithosphere. That could make it easier to bend, and that will really initiate the plate tectonics. Honestly, there's a lot of conversation going on over here, and people have been modeling. But I think we need some kind of different type of data. That's what I taught Jim and then kind of my Zoom time. But we need some type of a different kind of observation to progress this field of the initiation plate tectonics problem. That's all I can say for now.
Other students or Carl? James. One of you.
Okay, just a little question. You didn't really touch on it, but I think I know where you were going to go with it. Can you talk a little bit about the internal heat budget, how the differences would distribute the heat difference? Is there any role? I have a problem with radioactivity and heat budgets, and given the later inclusion, is there more kinetic energy involved in this? Or?
Yeah.
Do you understand my question? I'm sorry, it wasn't the best question.
Yeah, so there. Right now, what I'm thinking over here is a 30,000 year time scale. So for this time scale, radioactive elements doesn't really matter. but also it kind of does affect how it gets distributed among the different reservoirs. Yes, especially if it's a case that, so what I've showed over here was kind of homogeneous, so it doesn't really matter. But if it was a case that was kind of melt migration was efficient, we see it could be kind of trapping a huge amount of radioactive element in a kind of a deep mantle. That would really alter how core mantle interaction will take place and how the thermal evolution of basal magma, which that's kind of a popular idea for Venus recently, but those evolution take place. So it has a significant effect on the thermal evolution. I don't think people have really explored that. It's something that should be done. I'm not really answering your question because I don't think people really have a good answer to it, but it does matter. Yeah.
So your conclusion about the potential for there being a faster rate of plate tectonics. Now, I'm assuming you can model that, but is there any physical evidence that you can support that?
So I believe it happened because there's one data saying that the interpretation of that one data can say that there was a really efficient recycling of crustal material. So the crust was forming, it was forming really rapidly, and it was recycled really rapidly. And in order to have that, I believe we need a really fast plate tectonics. But it's an early Earth business. So to give you a sense, we only have a very small number of data, and the interpretation can be different. So some may argue this data does not argue for a plate like rapidly efficient crustal recycling, and that's also the case. So I have some evidence for that, but I do have to admit there's also another interpretations, and we need better data, more amount of data to kind of narrow down whether this was actually the case for the early Earth.
James.
So all these like small impactor cores that might be kind of embedded in the upper portions of the mantle. Does all that iron metal get oxidized to FeO, or does any of that, do you think any of that iron metal would survive to today?
So probably a huge amount of them will leave the mantle because it could get oxidized during some stages, but when it reacts, the deep mantle, probably like a disproportionate reaction. That's like Fe2 plus moves to Fe and Fe3 plus, and Fe can get sucked up. That kind of reaction happens. So most of them will probably leave. And the siderophile element itself can still stay in the mantle because there's such a massive reservoir of silicate that can kind of accommodate those. So probably iron, because we don't see that much metal in that present-day mantles. That's unlikely the case. But so probably those will leave the mantle and go to the core. But elements that brought with it will stay in the mantle. That's kind of what I think.
And so those kind of small planetesimals, they have to be somewhat volatile rich when they're impacting?
So that's the thing I really kind of conveniently not discussed during this talk. So I kind of assumed that the planetesimal thing was like was kind of just coming in and thinking about what was going to happen afterwards. I think what I'm kind of doing now and tackle next is what was the building block like? Those also planetesimals also have a magma ocean, have fractionation. It could have kept volatiles. It couldn't have. Some of them probably kept, some of them not. Not just volatiles. Some may lose silicon or like those kind of very refractory elements. It's being suggested to be lost from these planetesimals. It's kind of fascinating. I'm not sure it's true, but it's being suggested. So I want to model those and then kind of fed back to these kind of models to get a full picture of how planet formation happens from like day one to moon forming giant impact. That's kind of what I would like to envision doing. Yeah.
So you have this figure. I was interested in your thermodynamic model for the melts that are forming here. I guess, are the experiments that are that's based on, do they account for water? And so how well do you actually know the density of those somewhat hydrous melts? And then I guess related to that, how well do you know the partition coefficient of water and high pressures?
Thank you for the question. You were pointing my weakest point over here. And the thing is, okay, I would start defending my stuff because I think what I did at least kind of is the state of the art because there has to be a lot of experiments and nobody has really incorporated in this kind of depth. So that's what I tried to do. Of all the available experiments on like melting, partition coefficient, that's all being fed over here. What doesn't exist is the effect of hydrous mineral like water. Of course, some small amount of water, we know at the shallow mantle that it depresses the solid a specific amount. It changes the partition coefficient. But unfortunately, those experiments do not exist at deep mantle conditions. So my office mate is working on it from a first principle ab initio calculation. So if those come out, I would definitely think about it. And I suspect it can be really important. But that's kind of the next stage, kind of collaboration with high pressure mineralogists to kind of advance this field further. I think I did my best from the present day available data, but obviously we don't have enough data to kind of make a full argument, and that's where I'm heading to.
Well, if there's no other questions, let's thank Yoshi.
Thank you.